So if I may start, today's presentation is not so much regarding research, but I want to talk about an agenda that is like really important. I think a few of us has been discussing it. Of course, things are not, this is so new that we are still struggling to make sense of it. But one of the big things that we have been working on now is to create some benchmarking example. And of course, there's a very good reason to do so. And I'll talk about it later. So this presentation, as I said, is to start from a really big picture and then get down to specifics. And one of the purpose is to invite the speakers to try out some of these examples. And also the other thing is to get the audience to give us a more comments, how we can make the examples more realistic. So this is roughly what I'll be doing for the next 40 minutes or so. And certainly, I think Professor Yoshida and Professor Shuku has been spending a lot of time to organize this forum for us. And this is also supported and organized by TC304, which all of you know, and also the advanced retrofit technology, part of Tokyo City University. So thank you very much for this invitation. Maybe I can start right down to the picture. We've been talking about this Geo 4.0 agenda, and it's obviously related to how in the world geotechnical engineering can connect to industry 4.0. This is ongoing in all industry. The connection is not clear at this point in time. And of course, there are many reasons that we can talk about. But let me talk about a few points. I think what is missing, and we need to build this up very quickly, is that I think geotechnics needs to be, more of us needs to be working on what I call data-centric geotechnics. And what does that mean? To me, it simply means that if you're working in this area, you got to adopt what I call a digital-first agenda. You got to think like that. If not, you're not going to make any headway. And I can give you one example of how I felt what is a digital-first example. So it's very simple-minded thinking. If you're working in this area, you should definitely be thinking how you should create a method that can make sense of actual data. Of course, a lot of people are working on methods where you are modifying data to make sense of the method, the reverse. That is also very useful. But our entire practice now is based on us working on method as a primary method-centric kind of a strategy. And so I think what is lacking now is people working on method that will make sense of actual data. So it's a matter of rebalancing, not necessary to say that any methods are not useful. If we agree that this Geo 4.0 is targeted at Industry 4.0, then everything must be evaluated based on whether it's fit for practice. So this must be something that we must accept. So it can't be research at all, in my opinion. And finally, what I thought is very important is that if it's fit for practice and all practice is based on decision making for a specific project at a specific site, the question we have to ask ourselves is whether any of this method will be useful in that very specific sense. So we can talk about that later. So let me just share with you my view about what we've been doing now. A very powerful method, and certainly it's not in geotechnics, but it's underlying all sciences, what we call physics-based model. You have a model, and one of the most popular would be finite element models. To use the model, you need data. So the model is useless if you have no data, but the data is specific to that model. So I'm just using example, very familiar to everybody, such as shear modulus, undrained shear strength. It doesn't matter. The model itself dictates what kind of input data you need. You have real world data, can be anything, right? It can be data you collect from the site. It can be monitoring data. It can be remote sensing data. So you collect data of all kinds, and data are created because of availability of hardware, or because the equipment has been developed in other industry. Data are not collected to feed a particular model. I think that's quite clear to all of us, although we do that as well in our site investigation. To use your physical model, you need to think of a way of somehow interpreting real world data. The real world data will fit into your model. I know there's a huge amount of discussion on how we can do that. And on top of that, to get it to work, we need to do calibration. This is another set of data, maybe from load test, performance test data. You want to get your output to match. You want to get your model to produce the right kind of answer. You need calibration, you need judgment. So this is a rough summary of how I look at a physics model purely from the viewpoint of data requirements. There are other aspects of physics for sure. But today we are talking about data alone, right? Let's talk about data-driven model. What does that mean from my perspective? I think one of the most a well-known method would be neural net. It doesn't have to. I'm just using example. A neural net is based on an input layer. If you have real-world data, the model is actually trained to work with your real-world data. So you don't have to interpret real-world data to feed your model. So this learning and training is very important. In fact, that's why we are creating benchmark examples. Because this idea about learning and training is not as straightforward as all of us would like to think. And so this part is actually what I'm presenting this afternoon. So just to summarize a little bit what I thought we need to do if we want to go in this direction. And first of all, as I've emphasized, we need to consider data first, method second. In fact, if at all possible, we should look at real data. That's not easy, by the way. We should look at the value, and value in geotechnical engineering simply means decision making. You make a decision about a project, and this is done at a specific site. So far, to my knowledge, no one make a decision about all projects in Japan or Singapore. No one does that. It's always one project. The site can be a very big site. It can be a very small site. One thing we need to do is certainly to improve the compilation of data. Because without data, this agenda cannot proceed, and therefore databases are important. This is something TC304 is doing it, but to promote the collection and compilation of data, we actually need to consider client confidentiality. This deals with data anonymization. So this has nothing to do with method, but you want to promote data sharing. You need to consider bad data. I'll talk about that later. You need to consider data that is not so good. I call them ugly data. I'll talk about that later too. This is important. Why you need to consider what I call ugly data. Overfitting is one of the most difficult problem in data-driven methods. They have a tendency for overfitting, and that also explains why we have a benchmarking example, because that will consider validation data set. The last part we didn't do, of course, is that if you use data-driven method, they are not explainable to a human being compared to physics. So there's a question here. How does human judgment, how does a human engineer interface with your data-driven method? I think that's an important question. We haven't actually gone anywhere in this direction. So that's how I visualize what we need to do to make this what I call data-centric geotechnics. The whole agenda works. So that's to give you a very broad overview, right? Of course, today I'm just going to talk about site characterization, because nothing that we said will work if we don't look at site characterization, since our projects must be based on a particular site. And so this is a topic that we've been working on, which I'm very interested in. So let me define very quickly how we see a data-driven site characterization. So this is a subset of this broader agenda of Geo 4.0. I think it's just simply a way of characterizing your site using site-specific data. And as an engineer, if I'm trying to characterize a site, most engineers will not consider site-specific data alone. They will look for site in books. They will look for site data, maybe in neighboring sites or from their personal experience working for other projects. This definition is based on existing practice, so it's not invented by me. Any reasonable engineer will use all data, not just site-specific data. The tricky thing is, how do you combine site-specific data to data that don't belong to that site? Anyone would know that they are not identical. But again, I want to emphasize that this is an area where we need to look at data from routine projects. That will be the constraint of the, or I said rule of the game. So you cannot be collecting data from special research projects where you collect a lot of data. I think that will not make your method effective in practice. So you got to live with what we have in practice. That's the first rule of the game. Second rule of the game, if you're approaching it from data-driven angle, then you're basically looking for a model that's trained by actual data. I'll be explaining this subsequently as I present the benchmarking example. And lastly, since we want it to be fit for practice, it must be computable in 3D. Because our problem is 3D, right, intrinsically. So we can't avoid this. And this is actually very difficult. I'll show you later. All of you will know that three-dimensional problems are not just large, but complex. So it's not so simple. Recently, we have wrote a paper about some of the challenges. If you think in this angle, there will be at least 3 challenges you need to consider, but this is not the topic today. Today, I want to talk about ugly data because this is connected to benchmarking. It's very important for us to understand how do we define ugly data. As I said, we have a paper in Georisk, if you're interested in more details. But without reading this paper, let me do a very quick summary. How we imagine the universe of data. Well, the best data you can get is called godsend. So there's a supernatural force that gives you an answer. Well, if you have godsend data, you actually don't need to do any design because the answer is given to you. So that will be one extreme. The other extreme will be bad data. Bad data is simply defines data that has no value to your decision. In fact, it could be even counterproductive. Much of our geotechnical engineering has been focused on collecting good data because our model physics, if we go with a deterministic approach, we need good data. So this idea about physics and deterministic physics will force us to use good data. If not, the answer don't make sense since you cannot deal with uncertainty. So it's basically good data is defined by data that you can use directly for your model and cite. So you apply to maybe high quality block sampling, high quality laboratory tests to get exactly what you want under the correct boundary conditions. But no matter how well you do it, you cannot characterize a site spatial variability. So that defeats the purpose of all deterministic physics because the site is unknown, right? Well, ugly data is just between good and bad. Ugly data means data that you have, whatever you have. It can be anything, right? So it doesn't fit your needs. What is important in this classification is the amount of data. Of course, godsend data, you have none. This is just an abstract, extreme. All of us would know that good data, and that is something well known by all geotechnical engineers, good data is very, very limited. So if we stick to the idea that we only use good data, the whole idea about Geo 4.0 and data-centric geotechnics cannot work. So that's a simple conclusion. You cannot work because there isn't enough data. If you talk about ugly data, of course, you have a lot. The only question is how to make it useful, right? But you have a lot. A lot doesn't mean it's useful, by the way. So we just start with the premise that if you accept the use of ugly data, your Geo 4.0 agenda has a chance of working. So it's not known at this point in time whether it will work, but at least there's a chance. Well, bad data is not the same as ugly data. I want it to be very clear. And as I said, I define a bad data to be anything that is worse than no data. So there's a clear definition. You need to remove this bad data in your decision making. How to do it, of course, is a research question. It's not easy at all. So for those of you who are not like geotechnical engineers, maybe I just show you some idea about the real data that we had. So this is a paper that I did with Professor Zhang and Professor Huang from Tongji. But the idea is to give you some idea what is the size of a site. So that tells you what is the size of the site. More importantly, it tells you the kind of number of tests we do in one site. So without me going into great detail, you could see that the number is quite small. You don't have a boreholes and cone penetration test, vein shear test. Certainly, you don't have all these tests that you do at every 5 meters. Just an example. I mean, the site is the orange bar represents 50 meters. So this is a rather typical situation. This is a typical situation of the kind of data that you have. So it's quite clear at this point in time that you don't have a lot in a single site. And also the blue boxes represents data that you never collect. So having empty boxes is again not uncommon, right? This happens all the time in all site investigation. Of course, you don't collect simply because some of them are expensive. So you don't collect data, for example, like CPT, right? Cone penetration test, you collect maybe every 2 centimeters. You don't do that if you are collecting a soil sample, as an example. And so in my past presentation, I've been sharing that this is one possible definition of ugly data. I call that a music 3x. Multivariate because you collect more than one data, that's clear. Uniqueness is actually fundamental to geotechnical engineering because our sites are considered to be different. How different has never been quantified, by the way. We just assume that they're different because the geology is different. It's sparse. This is one of the biggest criticism on reliability-based method. So engineers always said that reliability-based method cannot work because there's not enough data. Incomplete, I've just shown you the table, why it's incomplete. Corrupted means bad data. You need to do something to remove it. So that's what it means. And of course, 3D spatial variation is intrinsic in our geotechnical data. This is something we have to accept if you're working in a geotechnical domain. This roughly captures what we're working in now. It's not complete, but it's already very difficult. In case you are thinking that why don't we add on more complexity and add more attributes, but there's no solution that we have now that can attack a music 3x in 3D in full. I'll talk about that later. Uniqueness, this is a real set of data just to show you that uniqueness is very difficult because we have a set of global database. These are the gray circular dot. And then we have the triangular dot representing data in Shanghai. The Shanghai data is embedded in the gray cloud, but identifying this so-called site uniqueness or Shanghai is not so simple, just by looking at this picture. Of course, if you are really ambitious, you can go from good. As I've said, good is deterministic. By magic, you can measure to the 6th decimal point, and all of us would know this is unreal. So this doesn't match reality. We got no such data as deterministic. Probabilistic is quite likely. It means that your data comes in a distribution. So I've been doing that for the past 50 years. It can get uglier, right? Because your data can be imprecise. Instead of having one distribution function, you have a family of distribution function. I'm using example only. Or you may have almost nothing other than an interval. You only got 2 numbers. You don't know what happens in between the numbers. An interval is not a uniform distribution, just to be very clear. And so on and so forth. You can censored data, truncated data, missing data. Missing means you got nothing. And then you got non-numerical data. It can be ordinal data, which are rank. I'll show you an example. It can be nominal data where it is just qualitative information. For example, maybe the different kinds of rocks, metamorphic rock, igneous rock, and sedimentary rock. These are nominal data. There's no ranking between these words. Let me show you a very simple example of what I meant by ordinal data. Using this geological strength index. This is a Hook and Brown, very classical. Again, without talking about the details, right? You want to compute the GSI, you need to know what is the so-called the structure rating, whether your rock is massively, disintegrated or is it intact. You need to know the surface condition rating of your joints. All these are basically ordinal data. They are not numerical data. In fact, in this particular paper, the suggestion is that your surface condition rating can be a function of a weathering rating, infilling rating. And this itself, this equation you see here is a function of ordinal data. So this exists a lot, particularly in rock engineering. And unfortunately, we have very little research in this direction, dealing with ordinal data. So it can get really ugly, but we haven't been working on this. What we've been working on is what I call big indirect data. And this is a valuable source of data, right? I've just mentioned that all engineers will consider data that is available on their shelf, in their past consulting projects, or on their hard disk. These are data from other sites, other applications, but they are not applicable to your particular project of interest. So that is our clear definition about big indirect data. What can we do, right? I mean, just using this analogy, big indirect data is like understanding the whole population. So it's like you trying to understand the behavior of your student in the entire class. That will be big indirect data. Based on the behavior of an entire class of students, can you understand the behavior of one student? The behavior of one student is not the same as the entire class, by the way. So would that be a connection? Clearly there is, but the connection is not direct. So in other words, we are of the opinion that big indirect data from other site is useful for your site. This assumption is not wrong because it's being done in all practices now. So all engineers use it. As I've mentioned, currently they are doing it based on judgment and based on qualitative appreciation. So there's no quantification of how to connect a beat and a site-specific data. We have been doing that, myself and Qian Ye has been doing that since 2012. So the database exists and they are openly available on TC304 website. And we'll be encouraging people to download the database and use it because this is a source of actual data. Recently, we're happy to see that the other authors are doing it for their own country. And we have been doing it for sand and rock. Last year, we've been doing this for performance data such as load test. So we've been also moving in another direction. And we have actually published a book on this. So it's enough at this point in time to know that we have a lot of data. So that the assumption that you have no actual data is wrong. So there's a lot of actual data. And I feel that all of us should come together to see how we can make good use of actual data. So that brings us to benchmarking, why we need it. Benchmarking is not invented by us. It's widely used in the machine learning community. And the purpose of benchmarking is very simple. You want to create examples where you can, performance matrix where you can do competitive evaluation of methods. With this competitive evaluation, I think our area can move faster. This is something that Takayuki and I are very interested to accelerate the progress in this area. Of course, as I've said, site characterization being such an important problem, we thought we should do it. In fact, that's why this forum is being held, to explain why we need to do benchmarking seriously, because this is missing at this point in time. You will let us know what is the advantages and disadvantages of all the methods that we are doing now. I'm sure the methods are good and not so good for different circumstances. It's unknown at this point in time because we cannot compare on a uniform basis. And a lot of the methods are not evaluated to see whether they fit for practice. I'll explain what is meant by fit for practice in a very specific way. This is what we meant by fit for practice. Firstly, the method must be able to apply to realistic ground. Two things we are looking at now in the creation of our benchmark example. Realistic ground means that it must be big enough to be realistic. The stratigraphy should be somewhat realistic. It should also apply to a realistic range of grounds because your method cannot apply to one. Because again, if you accept that our site are unique, It simply means that any method we develop must, if it's applied to practice, it must apply to different sites. It cannot just be good for one site, like in other words, that will not be realistic again. It should apply to properties that are realistic. It should apply to training data set that are realistic. I'll talk about that later. So the training cannot be unrealistic, then the method cannot be used. And then most importantly, the validation, the performance matrix must be evaluated for fit for practice, not research. So the method should be evaluated. Can it be adopted into practice, let's say tomorrow? And not for, to us, not to be, because we really need this method to be shared with practitioners and show the value to practitioners, I think quite urgently at this point in time. So let me go through over the next 10 minutes that I have on a set of preliminary proposals. So this is something that we've been working on. It is not final, but I think it gives you a sense about what we're trying to target. And we hope to get your comments, whether it can be adjusted or it should be improved in a very specific way. I want to show you a very simple, this is coming from Singapore. Our Urban Redevelopment Authority basically develops all buildings in Singapore. And they state that the minimum site area for flats and condominiums is about 1,000 to 4,000 meters square. I think these numbers will tell you that the size of the site has to be something like maybe 20 by 50 meter, or roughly of that range. So this gives you a sense what would be the site area. As what Yoshida-san has presented, our current proposal is a fairly small example. So this is not a building, maybe it's a shop house. 20 by 20 meter is smaller than 20 by 50 meter, and 10 meter is not very deep for those of you who do foundation engineering. But I just want to point out that even for this preliminary example we've set up, and we created a grid, because the purpose of this exercise is for us to estimate the properties in the grid. Already it produces 40,000 unknowns. If you assume every point in the grid is unknown, right, that you're trying to estimate. And as what Yoshida-san has shown, we start off with fairly simple stratigraphy, but they get more and more complex. Starting from G1, which is horizontal ground layer, all the way G4, where you get discontinuous layer, constant properties, and properties where there's a linear trend. I can imagine that we can have more complex examples in the future, but we thought this is already challenging enough. And it's kind of simple for us to try this out. Our data only consists of CPT data at this point in time. So it's only bivariate, cone tip resistance, and sleeve friction. We have adopted some parameters that we think they are realistic, but again, it could be improved. But this information that we use is based on what we know in the literature. So they are not numbers that are disconnected from reality. I mean, just to show you very quickly, this is the G3. This is a synthetic data set, right? So this is G3. G3 is inclined layer linear property trend. So this gives you a sense about the cone tip resistance and the sleeve friction. Simulated data compared to real data elsewhere. Well, there are some semblance. This is to show the G3 synthetic data on your famous Robertson chart. Again, I think there's some semblance between the data simulated and the real data. So we actually considered that this is there's some semblance to reality. We have actually fixed the water table at 2 meters. So this one is deterministic. We have created 3 training sets, T1, T2, T3. T1 is the most likely, in my opinion, because the site is very small, 20 by 20 meter. So T1 has 3 CPT. T2 has a 6. And then T3 has 7. The difference between T2 and T3 is an orange CPT that's close to the middle CPT. So we have T1, T2, T3. T3 is not likely in practice. There are just too many CPT. We have created validation data sets in blue. And so the purpose of this validation data set is to check how the method is performing at different location of the site. So therefore, the coverage is quite uniform. The validation data set is not used for training, by the way. So it's treated as being unknown. It's unknown data. You cannot use it in your method. So again, this is just to share with you what will be the training data for a G2 stratigraphy, which is inclined layers with constant trend. And T2 is basically your middle training set with 6 CPT sounding. So you could basically see the training set as far as the cone-tip resistance is concerned. You can show the same for the slip friction as well. In total, based on this very simple proposal, there will be 12 benchmark example because you have 4 possible ground type and you have 3 possible training set. And I think just based on my explanation, it's very clear to all of you that the problem difficulty gets higher and higher from T3, T2, T1. T1 only have 3. And then the ground becomes very difficult because by the time you reach a G4, your layers are discontinuous. You don't have continuous layer. I'm going to skip this because of time. I'm just saying that I'm using a particular technique called lasso to compute the some values to show you how we do our performance evaluation. So because of time, I'll skip it. Just to let you all know that lasso is a method that is being used to identify soil layers. It's not being used for number 2, engineering properties. But we can use it as a simple technique to check what will be the performance matrix. We have 2 very simple performance matrix, which is obvious. One is the root mean square error between what is known. So this is a real data from validation. X is basically your estimation using your algorithm. So you can do a root mean square error. We also check the identification rate because you want to know whether you're identifying the soil type correctly. Root mean square is to identify the soil properties. Identification rate is to identify the soil type. So the 2 are distinct. And the problem is the difficulty is not the same. Identification rate is not perfect, but it's kind of easy if you have a 3D mesh to do identification rate. But I wanted to show you that it's not perfect because these are 2 examples where the identification rate is the same. There are some errors. But the second example, which is a part B, you have problems. This error is important because this error creates artificial slope stability problems because you got artificial weak layers. Although the layers are thin, it can create effect on some problems, such as a slope stability. So identification rate is not perfect in terms of a relationship to the mechanics, but it's simple enough that it can be computed easily. This is an example of the result coming from G-Lasso, showing you the comparison between the actual data. Why? So this is the validation data set. The dashed line is the so-called estimated value using your data-driven method. And the orange line represents the theoretical layer location. So you need to get the property correct. You need to get the layer location correct. Due to time, let me skip to the last few slides. We wanted to also improve our performance evaluation by comparing against what we call 3 reference methods. The first one we call it a divine method. A divine method because we assume that the trend is known. Of course, the trend is not known, but the trend is known because this is a simulated example. If you assume that the trend is known, then your prediction, the error between your prediction and the actual answer will be just the theoretical standard deviation. In the case of a naive predictor, what you do is that basically you take the global mean. So this is something an engineer can do. They take the training set, they take the mean of the training set. The mean of the training set is your predictor. This is the most naive method. If your method cannot outperform the naive method, it's useless, in my opinion. The third method is something that some engineers will use where you take the training set, you perform, say, linear regression. Not very difficult. And then, of course, you end up with a regression error. So this is an example of a naive method. You basically take the global mean value, and then based on that, using the Robertson chart, you can roughly divide into 3 layers. There's a bit of human judgment involved. Based on each layer, you can compute the global mean, and the global mean represents your predictor. So this is a naive predictor. And then you can calculate the RMSE. So I just wanted to show you what is the comparison between a lasso, naive, and divine. You just look at the best RMSE. You notice that G lasso lost out to divine. That's to be expected, by the way. But maybe one day we can create a method that can beat divine. Fortunately, G lasso outperforms naive. If not, then G lasso will be proven to be useless. So I think, I think Takayuki and I felt that we are lucky that we did not end up with a useless method. But I think this kind of performance evaluation could be very useful. I think I run out of time, so maybe I could just run to the last slide. I already said that the problem is currently small, 20 by 20 by 10 meters. If you want to go for a realistic size, 80 by 40 by 40, that will involve 1 million degrees of freedom. This already tells you that the 3D computability in 3D is not a trivial problem. So this will be an example of a medium and a large size of problem. You can see that this is a small problem. One interesting aspect of this that I wanted to work with, I wanted to work on my next step, is whether we can divide the big problem into smaller problem and then treat the smaller problem as a similar site. So can you use the information in the similar site to update your target site? You can do that. Maybe the big problem can be subdivided into small problem, and maybe your computation will not be so serious. I mean the computation problem in 3D, but this is just speculation at this point in time. I'll stop here. Thank you very much.